Tonight, we're going to explore what Voyager detected at the edge of our solar system. There are two spacecraft out there in the darkness, launched in 1977, built for a mission that was supposed to last only a few years. Voyager 1 left Earth on September 5th. Voyager 2 launched a little earlier, on August 20th. Each one weighed about 1,820 pounds, carried instruments from the 1970s, and was sent outward to study Jupiter, Saturn, and the giant planets beyond. Given those numbers, the story should have been simple. A short mission, a few planet flybys, a final signal, then silence. Yet instead, one of those spacecraft kept going until it reached a place no human machine had ever measured before. More than 11 billion miles from the Sun, Voyager 1 crossed the heliopause, the invisible boundary where the Sun's solar wind finally gives way to the material between the stars. And what it found there did something strange. It showed that the edge of our solar system was farther away than scientists expected. It showed that the boundary was moving. It showed that particles from deep space were slipping inward before they should have been. It showed that the magnetic field did something scientists had trouble explaining. And it showed that the space beyond the Sun's bubble was not empty, still, or simple. It had pressure. It had waves. It had structure. It had a kind of hidden weather, moving through a region so thin that it makes the best vacuum chambers on Earth seem crowded. This is what makes Voyager's discovery so unsettling. The spacecraft did not simply reach a line and cross it. It entered a strange borderland where the Sun and the galaxy press against each other, where solar particles fade, galactic particles rise, magnetic fields twist, and the definition of leaving the solar system becomes harder than it sounds, because Voyager has crossed into interstellar space. But it has not escaped the Sun completely. Far beyond Voyager, the Sun's gravity still reaches into the distant Oort cloud, a vast shell of icy bodies that may stretch thousands of times farther than Neptune. So the spacecraft has entered the space between the stars, while still moving through the outermost reach of the Sun's kingdom. That is the contradiction at the center of tonight's journey. Voyager reached the edge, and then revealed that the edge was only the beginning. By the end of tonight, you're going to understand what Voyager actually detected, why those measurements surprise scientists, and why the boundary around our Sun is less like a wall and more like a living, shifting shield around everything we know. Before we get started, if you enjoy calm journeys through deep space, take a moment to like the video or subscribe. It is a small action, but it helps this channel reach more people who enjoy slow, thoughtful explorations of the universe. Now, let's begin. To understand why Voyager's detection mattered so much, we have to picture the spacecraft itself. This was not a modern probe filled with today's computers. Voyager was designed in the early 1970s, before smartphones, before home internet, before most people had ever touched a personal computer. Its memory was tiny by modern standards. Its transmitter used less power than many household light bulbs. Its instruments were built for planetary flybys, not for becoming humanity's first working laboratory in interstellar space. And yet, decade after decade, it kept speaking. The signal had to cross billions of miles before it reached Earth. By the time scientists received it, it was unimaginably faint, a whisper from a machine so far away that light itself needed many hours to carry the message home. Every number makes the situation harder to believe. A spacecraft built for a short mission survived long enough to measure the edge of the Sun's influence. A probe with 1970s hardware, detected particles from outside the solar system. A machine launched before many of today's scientists were born became the first object humanity ever sent into interstellar space. That alone would make Voyager one of the greatest missions ever flown. But the deeper story is stranger than survival. Because Voyager did not just travel far, it traveled far enough to test the map scientists had drawn of the solar system's outer boundary. For decades, researchers had models. They had equations. They had ideas about where the solar wind should slow down, where the heliosphere should thin out, and where interstellar space should begin. Voyager turned those ideas into measurements. And once the measurements came back, the clean picture began to break. The first surprise was distance, then came motion, then shape, then the strange behavior of particles and magnetic fields. One discovery led to another, and each one made the edge of the solar system feel less like a clean border and more like a restless frontier. The launch window that made Voyager possible opened in 1977. At Cape Canaveral, NASA prepared two nearly identical spacecraft for a journey into the outer solar system. Voyager 2 launched first on August 20th, 1977. Voyager 1 followed a few weeks later, on September 5th. The numbers in their names came from the order they would reach the planets, rather than the order they left Earth. Voyager 1 was placed on a faster path. It would reach Jupiter and Saturn before its twin. Voyager 2 would take a longer route, but eventually continue toward Uranus and Neptune. Each spacecraft weighed about 1,820 pounds. That is roughly the mass of a small car. But instead of seats, wheels, and an engine, each Voyager carried cameras, scientific instruments, antennas, fuel lines, thrusters, computers, and a nuclear power source. The most recognizable part of each spacecraft was its large dish antenna. It was about 12 feet wide, roughly the height of a one-story room turned sideways. That antenna had one job that mattered more with every passing year. It had to keep pointing back toward Earth. Without it, Voyager could still travel through space, but it could no longer tell us what it was seeing. Extending from the main body were long booms that held instruments away from the spacecraft's own electrical noise. One boom carried magnetometers, devices that measure magnetic fields. Another held the radioisotope thermoelectric generators, usually called RTGs. These generators used heat from the natural decay of plutonium-238. That heat was turned into electricity. At launch, each Voyager produced only a few hundred watts of power, less than what many kitchen appliances use. Yet that small amount of power ran the computers, instruments, heaters, transmitters, and attitude control systems that kept the spacecraft alive. The mission was designed around the giant planets. Voyager 1 would fly past Jupiter in 1979 and Saturn in 1980. Voyager 2 would visit Jupiter in 1979, Saturn in 1981, Uranus in 1986, and Neptune in 1989. The original core mission was measured in years. Study Jupiter, study Saturn, return images and measurements. Then, as the power faded and the instruments aged, the spacecraft would slowly become quiet. That would have been a successful mission. By the early 1980s, Voyager had already changed what scientists knew about the outer planets. It had seen active volcanoes on Io. It had revealed strange details in Jupiter's storm bands. It had shown Saturn's rings as thousands of narrow structures shaped by gravity and motion. It had looked closely at moons that had once been no more than bright dots through telescopes. Then the mission should have become history. But the spacecraft kept working. The instruments stayed alive. The antenna kept finding Earth. The RTGs kept producing enough power. The tiny onboard computers kept accepting instructions sent from billions of miles away. Year after year, Voyager moved farther from the Sun. The planets fell behind it. Jupiter became part of the past. Saturn became part of the past. The familiar architecture of the solar system slowly gave way to darkness, distance, and charged particles streaming outward from the Sun. This is what makes Voyager feel almost impossible. It was a machine from the 1970s, still speaking in the 21st century. It was built before modern laptops, before smartphones, before home internet, before most of the technology now used to track it. And yet, while newer machines aged, failed, and were replaced on Earth, Voyager continued outward. By the time it approached the Sun's outer boundary, it had been traveling for more than 3 decades. By the time scientists confirmed Voyager 1 had entered interstellar space, the spacecraft had been alive for 35 years. A mission built for planetary encounters had become a working detector at the edge of the Sun's bubble. Its survival is remarkable by itself. But Voyager did not reach that distant region by endurance alone. Long before it crossed into interstellar space, its path had been shaped by a rare arrangement of planets, a pattern in the outer solar system that appears only once in about 176 years. Voyager reached the outer darkness because the planets happened to be arranged in a rare pattern. In the late 1970s, Jupiter, Saturn, Uranus, and Neptune were positioned in a way that allowed one spacecraft to visit them in sequence. This kind of alignment appears about once every 176 years. For mission planners, it was a narrow doorway in time. Miss it, and the same route would be gone for generations. The idea became known as the Grand Tour. A spacecraft could launch from Earth, fly to Jupiter, use Jupiter's gravity to bend and speed up its path, then continue to Saturn. From there, the same method could carry it farther outward. Voyager 2 would follow the fuller version of this route. It would visit Jupiter in 1979, Saturn in 1981, Uranus in 1986, and Neptune in 1989. Voyager 1 would take a faster path to Jupiter and Saturn. Its route would give scientists a close look at Saturn's moon Titan, then send the spacecraft upward, away from the flat plane where most planets orbit. That decision changed its future. Voyager 1 would give up the chance to visit Uranus and Neptune, but in exchange it would be thrown onto a path leading out of the planetary region entirely. This was possible because of gravity assist. A gravity assist sounds almost like a trick, but it follows simple physics. A planet is moving around the Sun. Jupiter, for example, travels around the Sun at about 13 kilometers per second. When a spacecraft approaches from the right direction, Jupiter's gravity pulls it into a curved path. As the spacecraft swings past, it takes a tiny amount of momentum from the planet's motion. Jupiter loses an amount of speed too small to measure in any practical way. Voyager gains enough speed to change the rest of its journey. It is like a small boat catching the pull of a huge moving current. The current barely notices. The boat leaves much faster than before. Without this technique, visiting the outer planets would have required enormous amounts of fuel. Every pound of fuel added to a spacecraft creates a problem. More fuel makes the spacecraft heavier. A heavier spacecraft needs more fuel to accelerate. Then that extra fuel adds even more weight. This is one of the hard limits of rocket travel. The Grand Tour avoided part of that trap by using the planets themselves. Jupiter became a giant moving engine. Saturn became another turning point. Their gravity did work that no rocket launched from Earth could have carried inside its tanks. This is why the Voyager mission was so carefully timed. The spacecraft had to reach each planet at the right angle, at the right speed, and in the right year. A small error early in the journey could become a huge miss billions of miles later. Voyager was moving through a solar system where everything was in motion. Earth was moving. Jupiter was moving. Saturn was moving. The spacecraft was moving. The mission was less like aiming at a target and more like threading a needle, while the needle itself was racing around the sun. When Voyager 1 reached Jupiter in March 1979, it had already traveled hundreds of millions of miles. Jupiter's gravity bent its path and gave it the speed it needed to reach Saturn. When it reached Saturn in November 1980, Saturn's gravity changed its path again. After the Titan flyby, Voyager 1 was sent above the plane of the planets. From that point on, it was no longer moving from one planetary stop to another. It was leaving the main road. The giant planets had done more than reveal storms, rings, moons, and magnetic fields. They had turned Voyager into an outbound messenger. Behind it were the worlds it had been built to study. Ahead of it was a region no spacecraft had ever reached. The planets were fading into the past, and the sun's invisible boundary was waiting far beyond them. Beyond Saturn, Voyager moved into a darker and quieter part of the solar system, but it was still not moving through empty space. Even far from the planets, the spacecraft was still inside something vast. It was inside the invisible bubble created by the star at the center of our system. The sun is not only a ball of light and heat, it is also constantly shedding material into space. From its outer atmosphere, called the corona, the sun releases a stream of charged particles. Most of these particles are protons and electrons. A proton is a tiny particle with a positive electric charge. An electron is much smaller and carries a negative electric charge. Together, they form plasma, which is what gas becomes when its atoms have been pulled apart by extreme heat and energy. This stream is called the solar wind. Near Earth, the solar wind usually travels at hundreds of kilometers per second. That means it can move faster than 1 million miles per hour. It does not blow like air on Earth. There is no thick atmosphere carrying it. Instead, it is a thin flow of electrically charged particles spreading outward in every direction. The solar wind begins in the corona, where temperatures can reach more than 1 million degrees Celsius. At those temperatures, the sun's outer gas is so energetic that some of it escapes the pull of solar gravity. It streams outward past Mercury. It passes Earth. It passes Mars, Jupiter, Saturn, Uranus, and Neptune. Every planet orbits inside this moving flow. Earth is protected from the worst of it by its magnetic field, which guides many charged particles around the planet. That protection helps create auroras near the poles, where some particles follow magnetic field lines into the upper atmosphere. But farther out, away from planets and magnetic shields, the solar wind becomes the main environment of space. It carries part of the sun's magnetic field with it. Because the sun rotates about once every 27 days near its equator, that magnetic field does not stretch outward in perfectly straight lines. It forms a wide spiral pattern, sometimes called the Parker spiral, named after physicist Eugene Parker, who helped predict the solar wind in the 1950s. The farther the solar wind travels, the more space it has to fill, so it becomes thinner. Near Earth, a cubic centimeter of solar wind might contain only a handful of particles. That is already far emptier than any air a person could breathe. Far beyond Neptune, the flow is even weaker. But it is still there. It still carries pressure. It still carries magnetic fields. It still marks space as part of the sun's domain. This is the heliosphere. The word comes from Helios, the ancient Greek name connected with the sun. The heliosphere is the enormous region filled and shaped by the solar wind. It is not visible like a soap bubble. A telescope cannot simply look out and see a glowing shell around the planets. But it is real because spacecraft can measure the particles, fields, and radiation inside it. In a simple picture, the heliosphere is like a protective bubble around the solar system. Inside it, the sun has a powerful influence over the space environment. Outside it, the galaxy begins to take over. That bubble matters because the Milky Way is full of galactic cosmic rays. These are fast-moving particles that can come from violent events such as exploding stars. Some cosmic rays carry enough energy to pass through spacecraft walls, damage electronics, and affect living tissue. The heliosphere helps reduce how many of those particles reach the inner planets. It acts like a shield, although an imperfect one. Some cosmic rays still enter, but many are slowed, scattered, or redirected by the solar wind and the magnetic field carried through it. For Earth, this distant bubble is part of a much larger chain of protection. First comes the heliosphere, then Earth's magnetic field, then the atmosphere. Together, these layers help make the surface of our planet far safer than raw space. Voyager was traveling through the outer part of that first shield. It was moving through the fading reach of the solar wind. The planets were far behind it, but the sun's particles were still flowing around it. The spacecraft had not yet reached the place where the solar wind finally loses the battle. A bubble cannot expand forever. Somewhere far beyond the planets, the outward push from the sun has to meet the thin material between the stars. Far beyond Neptune, the solar wind keeps traveling outward. It becomes thinner with distance, spreading into a larger and larger volume of space. But it still carries pressure. It still carries charged particles. It still carries the magnetic field of our star. Eventually, that outward flow reaches the material between stars. That material is called the interstellar medium. The word medium simply means the substance that fills a space. On Earth, air is the medium that sound travels through. Between stars, the medium is extremely thin gas, plasma, dust, magnetic fields, and high-energy particles. Most of the gas is hydrogen. Hydrogen is the simplest element in the universe, with one proton and one electron. In some regions, the hydrogen is neutral, meaning the proton and electron remain together. In other regions, the atoms are broken apart into plasma, with charged particles moving separately. Near our solar system, the interstellar medium is thinner than almost any vacuum humans can make in a laboratory. A cubic centimeter of local interstellar space may contain only a fraction of a particle on average. A cubic centimeter of air near sea level contains roughly 10 billion molecules. That comparison is almost impossible to picture. It means the space between stars is so thin that a person could pass through it forever and never feel a breeze. Yet across billions of miles, even this thin material matters. It has density. It has motion. It has magnetic pressure. It has cosmic rays moving through it from distant explosions and other violent events in the galaxy. The solar wind has to push against all of that. The sun is also moving through this environment. Our whole solar system travels around the center of the Milky Way, completing one wide orbit in roughly 225 million years. But compared with the nearby interstellar gas around us, the solar system is moving at about 26 kilometers per second. That is about 58,000 miles per hour. From the sun's point of view, the surrounding interstellar material flows toward it like a faint galactic headwind. The solar wind pushes outward. The interstellar medium presses inward. Somewhere between those two pressures, a boundary forms. That boundary is called the heliopause. The heliopause is one of the most important invisible borders in our cosmic neighborhood. Inside it, the solar wind still dominates. Outside it, the particles and magnetic fields of the galaxy become stronger than the flow from our star. It is easy to imagine this boundary as a shell, but it is shaped by motion, pressure, magnetism, and time. The sun is moving through the local interstellar cloud, a warmer, thinner region of gas that our solar system is currently passing through. That cloud is only a small part of the Milky Way, but it still presses against the heliosphere from the outside. The result is a boundary that changes with the strength of the solar wind and the conditions of the material around it. When the sun is more active, it sends stronger gusts of charged particles outward. Those gusts can travel for years before they reach the edge. When the solar wind weakens, the outer boundary can shift inward. This means the heliopause is a real physical boundary, but it behaves like a moving surface. It is shaped more like a pressure balance than a solid wall. A submarine deep under the ocean is surrounded by water pressure. A weather balloon in the atmosphere expands until the pressure inside and outside settle into balance. The heliosphere works on a far larger scale, with solar plasma pressing against the thin material between stars. Voyager was heading toward the place where those pressures meet. For decades, scientists could only study that boundary from far away. They could measure the solar wind near Earth. They could observe the glow of hydrogen beyond the planets. They could build computer models using plasma physics, magnetic fields, and estimates of interstellar pressure. But no spacecraft had ever touched the heliopause directly. Voyager was going to turn an invisible prediction into a real measurement. Scientists had an idea of where the boundary should be. They had an idea of what the crossing should look like. And as Voyager moved deeper into the darkness, that model was about to be tested. Before Voyager arrived, scientists had a clean picture of how this boundary should work. It was not guesswork in the casual sense. It came from decades of physics, spacecraft measurements near Earth, and computer models of plasma moving through magnetic fields. Plasma is what happens when gas becomes so energetic that many atoms are split into charged pieces. Because those charged pieces respond to magnetic fields, plasma can behave in ways ordinary air never could. Still, the basic structure seemed understandable. The solar wind would stream outward from our star. It would keep moving through the planetary region, past Jupiter, past Saturn, past Uranus, past Neptune, and into the dark outer reaches. Then, far beyond the planets, it would reach the first major boundary. That boundary was called the termination shock. The name sounds dramatic, but the idea is simple. The solar wind travels outward faster than certain pressure waves can move through it. In that sense, it is moving faster than its own warning signal. When that fast flow begins to feel the pressure of the interstellar medium ahead of it, it has to slow down suddenly. That sudden slowing creates a shock. A familiar version happens when an aircraft moves faster than sound through Earth's atmosphere. Pressure piles up into a sharp wave. In space, the material is much thinner, and the flow is plasma instead of air. But the same basic idea applies. Fast material runs into changing pressure, and the flow has to adjust. Scientists expected Voyager to see the solar wind slow sharply at the termination shock. The particles should become hotter. The density should change. The magnetic field should become more compressed and turbulent. It would be the first sign that Voyager had entered the outer borderland of the heliosphere. Beyond the termination shock, the spacecraft would move into the heliosheath. The heliosheath was expected to be a wide transition region. Inside it, the solar wind would still come from our star, but it would no longer be racing outward in the same clean way. It would be slower. It would be hotter. It would be more disturbed. Instead of streaming smoothly away from the center of the solar system, the plasma would begin flowing sideways as if trying to move around the pressure of the galaxy. Scientists pictured this region as messy, but still understandable. A turbulent cushion between the sun's bubble and interstellar space. The heliosheath would not be the final edge. It would be the space before the final edge. Then came the heliopause. This was the boundary Voyager was ultimately heading toward. At the heliopause, the outward pressure of the solar wind would finally balance the inward pressure of the interstellar medium. Inside that boundary, the space environment would still be shaped mostly by solar particles. Outside it, the galaxy would take over. The particle mix should change. Low-energy particles from the solar wind should fade. Galactic cosmic rays should rise. The plasma around the spacecraft should no longer be the same solar material that had flowed outward for billions of miles. The magnetic field was also expected to show a change. Inside the heliosphere, the field carried by the solar wind was shaped by the rotation of our star. Outside the heliopause, The field should belong to the local interstellar medium and the wider Milky Way. Scientists expected the direction of the magnetic field to shift as Voyager crossed from one region into the other. The model had a satisfying order: termination shock, heliosheath, heliopause, interstellar space. Each layer had a role. Each boundary had a signal. Voyager would move through them one at a time, and the instruments would tell scientists where it was. The distances were uncertain, but the pattern seemed reliable. The termination shock was expected somewhere in the far outer heliosphere. The heliosheath would stretch beyond it. The heliopause would wait farther out, perhaps around 90 to 100 astronomical units from our star. 1 astronomical unit is the average distance from Earth to the Sun, about 93 million miles. So a boundary near 100 astronomical units would sit about 9.3 billion miles from the center of the solar system. That was already a staggering distance. But it was still a distance scientists could model. The equations gave them a map. Voyager was about to fly into that map. And the first major crossing would show whether the map was right or whether the edge of the solar system was already beginning to behave in a way no one had fully expected. Voyager reached the first major boundary years before it reached interstellar space. This was the termination shock. It was the place where the solar wind finally began to lose its speed. For decades, the solar wind had carried Voyager outward through the heliosphere. It had streamed past the spacecraft as a thin flow of charged particles. Even far beyond Neptune, that flow still came from our star. But as Voyager moved deeper into the outer heliosphere, the solar wind began pressing against the material between stars. The flow could no longer keep racing outward in the same way. It had to slow down. On December 16th, 2004, Voyager 1 crossed the termination shock. It was about 94 astronomical units from the center of the solar system. 1 astronomical unit is the average distance from Earth to the Sun, about 93 million miles. So Voyager 1 was roughly 8.7 billion miles from the center of the solar system when it crossed that first boundary. That was already farther out than many models had expected. The boundary was supposed to be closer. Scientists knew it could move. They knew the solar wind changes with the solar cycle, the roughly 11-year rise and fall in solar activity. During more active years, stronger gusts from the sun can push the boundary outward. During quieter years, the pressure drops and the boundary can move inward. But Voyager 1 still found the termination shock at a striking distance. The sun's bubble was larger than the clean model had suggested. The instrument saw signs that the environment around the spacecraft had changed. The solar wind had entered a slower and more disturbed region. Particles became more energetic. Magnetic activity became more complex. Voyager had crossed from the supersonic solar wind into the outer borderland of the heliosphere. Supersonic means the flow was moving faster than pressure waves could travel through that plasma. After the shock, the flow became slower and more compressed. It was like a river that had been racing downhill and then suddenly ran into deep, heavy water. The river still moved, but its shape, speed, and behavior changed. For Voyager, that change marked the beginning of the heliosheath. The first layer of the expected map had been reached, but then Voyager 2 added a second piece of evidence. On August 30th, 2007, Voyager 2 crossed the termination shock. It was about 84 astronomical units from the center of the solar system. That was about 10 astronomical units closer than Voyager 1. 10 astronomical units is not a small difference. It is about 930 million miles. That is more than the distance from the Sun to Saturn. Two spacecraft had crossed the same kind of boundary, but they crossed it at very different distances. This mattered because Voyager 1 and Voyager 2 were traveling in different directions. They were not moving along the same path. Voyager 1 had been sent upward from the plane of the planets after its Saturn encounter. Voyager 2 followed a different outward route after visiting Uranus and Neptune. Together, they gave scientists two separate measurements of the same invisible structure, and those two measurements showed that the termination shock was not a smooth sphere wrapped neatly around the solar system. It was uneven. It was shaped by direction. It was shaped by the solar wind. It was shaped by the pressure of interstellar space pressing in from outside. The boundary was closer in some places and farther away in others. The heliosphere was beginning to look less like a perfect bubble and more like a flexible shield being pushed, stretched, and compressed by its surroundings. This was the first real crack in the clean picture. The order of the model still made sense. Termination shock first, heliosheath after that, heliopause farther out. But the details were already shifting. Voyager had found the first boundary. It had also shown that the boundary was not sitting at one simple distance. It changed, depending on where the spacecraft crossed, and distance was only the beginning of the surprise. The termination shock was not only uneven, it was moving. The termination shock was not fixed in place. It did not sit at one clean distance, waiting for Voyager like a border drawn on a chart. It moved. It expanded outward. It pulled inward. It shifted as the pressure from our star rose and fell across time. The reason was solar activity. The Sun goes through a cycle that lasts about 11 years. During active parts of that cycle, the surface and atmosphere of our star produce more storms, more eruptions, and stronger streams of charged particles. During quieter parts, the outward pressure weakens. Those changes do not reach the edge immediately. The termination shock sits billions of miles away. A disturbance from the inner solar system can take many months or even more than a year to travel that far. So Voyager was not only measuring a place, it was measuring the delayed memory of solar storms that had happened long before. This is where the clean model became harder to hold. Before the confirmed crossing in December of 2004, Voyager 1 saw signs that looked like it had reached the termination shock earlier. Around 2002, when the spacecraft was about 85 astronomical units from the center of the solar system, its instruments detected changes that suggested the boundary was nearby. The particles became more disturbed. The magnetic environment changed. The readings looked like the solar wind was beginning to slow. Then the signs faded. Voyager seemed to be back in the faster solar wind again. The spacecraft had not turned around. It had not moved inward. The boundary itself had shifted. A moving wave of solar pressure had pushed the termination shock outward, then allowed it to retreat. Voyager was like a person standing near the edge of a shoreline while the tide moved around their feet. For a moment, the water reaches them. Then it pulls back. Then another wave comes in. The person has not moved very far, but the boundary has crossed them more than once. That is a better way to picture the outer heliosphere. It is not a painted line on a map. It is more like a distant shoreline made of plasma, pressure, and magnetic fields. Solar storms are the waves. The interstellar medium is the deeper ocean pressing back from outside. Voyager was standing in the place where both sides could reach it. By 2004, the crossing became lasting. Voyager 1 moved into the region beyond the termination shock and stayed there. The solar wind around it was now slower, hotter, and more turbulent. But the earlier hints mattered. They showed that the edge was alive with motion. They showed that the spacecraft could pass through a boundary because the boundary moved over it, not only because Voyager moved across the boundary. That is a strange idea. On Earth, borders usually feel fixed. A fence stays in place. A coastline changes slowly. A national boundary remains on a map unless people change it. But in space, this boundary was made from moving material. It depended on pressure. It depended on magnetic fields. It depended on storms that began near our star and spent months traveling into the dark. A powerful burst from the sun could make the heliosphere swell. A weaker period could let the galaxy press inward. The entire outer bubble could breathe. This made Voyager's journey more complicated than a simple outward crossing. The spacecraft was traveling away from the planets at a steady speed, but the environment around it was changing. The boundary ahead of it was changing. The pressure behind it was changing. The particles passing over its instruments were carrying the history of solar activity across billions of miles. The termination shock had already shown two important things. It was uneven in shape, and it was restless in time. That mattered because the termination shock was only the first boundary. Farther ahead was the heliopause, the place where the solar wind would finally give way to interstellar space. If the first boundary could move like a shoreline around Voyager, the final boundary might be even harder to define. The final boundary was already becoming harder to picture. Voyager had shown that the termination shock was not sitting at one simple distance. It had also shown that the boundary could move as solar pressure rose and fell. But there was a deeper problem. The shape itself was wrong. For a long time, the simplest picture of the heliosphere was a round bubble around the planets. The sun sent the solar wind outward in every direction. The solar wind pressed against the material between stars. A boundary formed around the whole system. From far away, it was tempting to imagine something almost spherical, a glowing planet sized up to cosmic scale, with the sun near the middle and the planets tucked inside. Voyager began replacing that simple picture with something more complicated. Voyager 1 and Voyager 2 did not leave the solar system along the same path. Voyager 1 flew past Jupiter in 1979 and Saturn in 1980. After its close study of Saturn's moon Titan, it was sent upward from the flat plane where most planets orbit. That flat plane is called the ecliptic. It is the broad disc-shaped path where Earth, Mars, Jupiter, and the other major planets travel around our star. Voyager 1 moved above that plane. Voyager 2 followed a different route. It visited Jupiter, Saturn, Uranus, and Neptune, then continued outward below the plane of the planets. Together, the two spacecraft gave scientists two separate cuts through the heliosphere. They were like two needles passing through different parts of the same invisible fabric. If the heliosphere had been a simple sphere, the two paths should have looked more alike. The distances would still vary a little, because the solar wind changes over time, but the overall structure should have been fairly even. Instead, Voyager found a boundary that depended on direction. The reason is that the solar system is not sitting still. The Sun and all the planets are moving through the local interstellar medium. That motion creates pressure. It is similar to what happens when a person walks through still air. The air seems to move against the face because the person is moving through it. For the heliosphere, the effect is far larger and much slower to change. Our solar system moves through the nearby interstellar material at about 26 kilometers per second. That is about 58,000 miles per hour. From the point of view of the Sun's bubble, the material between stars flows toward it like a faint galactic headwind. That headwind presses more strongly on the front side. It compresses the nose of the heliosphere. Behind the Sun's motion, the bubble can stretch into a longer tail. This does not make the heliosphere a neat comet shape with a sharp point and a perfect trail. The real shape is affected by magnetic fields, solar activity, particle pressure, and the density of the local cloud around us. It is a moving bubble under pressure. The front is pushed. The sides are shaped. The tail extends behind. And every part of it can change as the Sun moves through slightly different material in the galaxy. This matters because Voyager was not simply measuring distance. It was measuring direction. Voyager 1 gave a reading from one part of the outer heliosphere. Voyager 2 gave a reading from another. The two measurements showed that the Sun's bubble has geography. It has regions. It has a front, sides, and a trailing direction. It has places where the pressure balance is different. It has places where particles and magnetic fields behave in their own way. The solar system's boundary was becoming less like the edge of a ball and more like the outer skin of something moving through a current. A boat on a lake forms a bow wave at the front and a wake behind it. The boat is solid. The water is fluid. The shape of the disturbance depends on motion. The heliosphere is similar in spirit, but made from plasma and magnetic fields instead of wood and water. Voyager had entered a structure shaped by the journey of our entire solar system through the Milky Way. The farther it traveled, the clearer this became. The boundary was uneven. It was moving. It was compressed in some directions and stretched in others. And once Voyager entered the region beyond the termination shock, those simple expectations would keep failing, one by one. After the termination shock, Voyager entered the heliosheath. This was the wide region between the first shock and the final boundary. It was not interstellar space yet, but it was no longer the same smooth solar wind that Voyager had traveled through for decades. Before the termination shock, the solar wind raced outward at hundreds of kilometers per second. After the shock, that flow slowed down. It became hotter. It became more compressed. It became more disturbed. The particles were still mostly from our star, but they were now moving through a region where the pressure of the galaxy was starting to matter. The heliosheath was expected to act like a waiting room. Behind Voyager was the faster solar wind. Ahead of it was the heliopause, the place where solar space would finally give way to interstellar space. Between those two places was this thick, turbulent layer. Scientists expected it to be messy, but understandable. The solar wind would keep flowing outward, but more slowly. Some of it would begin sliding sideways, pushed by the interstellar medium outside the bubble. Magnetic fields would be stretched and disturbed. Particles would bounce, scatter, and gain energy. But the basic identity of the region seemed clear. It was still part of the heliosphere. It was still inside the Sun's protective bubble, carried by material that had originally flowed away from our star. Voyager 1 entered this region after its confirmed termination shock crossing in December of 2004. Voyager 2 entered it after crossing the termination shock in August of 2007. Both spacecraft were now in a borderland. They had passed the first major marker. They had not reached the final edge. For Voyager 1, the journey through the heliosheath would last almost 8 years. That matters because the heliosheath was not a thin skin. It was a huge region of space, wider than the distance between several planets. A spacecraft moving faster than any human-made object had ever traveled still needed years to cross it. During those years, Voyager was surrounded by a strange mixture of familiar and unfamiliar signals. The solar wind was still present. The sun's magnetic field was still there, carried outward and twisted by rotation. But the environment was changing. The flow was slower. The particle readings were different. The pressure balance was shifting. The spacecraft was moving through the outer cushion of the solar system. A useful way to picture it is a river meeting the sea. Far upstream, the river has a clear direction. It flows one way. Its current is strong and recognizable. Near the mouth, the river begins to slow and spread. Salt water presses in. Waves disturb the surface. The river is still there, but the ocean is starting to shape it. The heliosheath was like that, except the river was solar wind, and the ocean was the galaxy. Voyager was drifting through the place where those environments began to mix. Scientists watched the data carefully. The cosmic ray instrument measured fast particles from outside the solar system. The magnetometer measured the strength and direction of magnetic fields. The plasma wave instrument listened for vibrations in the thin charged gas around the spacecraft. Each reading helped build a picture of where Voyager was inside the invisible boundary. At first, the story still fit the model. The spacecraft had crossed the termination shock. It was moving through the heliosheath. The heliopause should be farther ahead. Eventually, solar particles would drop. Galactic particles would rise. The magnetic field might shift. Then Voyager would enter true interstellar space. But the longer Voyager stayed in the heliosheath, the less simple the waiting room became. It was not just a quiet hallway before the final door. It was active. It was changing. It was threaded with magnetic structure. And as Voyager moved deeper into it, the first signs of the galaxy began appearing before the final boundary had opened. As Voyager 1 moved deeper through the heliosheath, the spacecraft began to detect a quiet change. The particles from the galaxy were increasing. These particles are called galactic cosmic rays. They are tiny pieces of matter moving at extreme speeds. Most are protons, the positively charged centers of hydrogen atoms. Some are heavier atomic nuclei, from elements such as helium, carbon, oxygen, and iron. They can be accelerated by powerful events across the Milky Way. A massive star explodes as a supernova. A shock wave spreads through space. Magnetic fields catch charged particles and whip them to enormous energies. Some of those particles travel through the galaxy for millions of years before reaching our solar neighborhood. By the time they arrive, they are moving so fast that they can pass through spacecraft walls, electronics, and human tissue. This is why cosmic rays matter. They are invisible. They are tiny, but they carry enough energy to damage atoms inside living cells. On Earth, the surface is protected by several layers. The heliosphere reduces part of the cosmic ray flow before it reaches the inner solar system. Earth's magnetic field bends many charged particles away. The atmosphere absorbs many of the particles that still get through. Voyager was far beyond those last two protections. It was inside only the outer shield made by solar wind and magnetic fields. Scientists expected galactic cosmic rays to rise as Voyager approached the heliopause. That part made sense. The farther the spacecraft moved from the inner solar system, the weaker the sun's shielding became. But the timing was strange. The rise began before the final crossing. Voyager 1 was still inside the heliosheath. It was still surrounded by slowed solar wind. It had not yet reached the confirmed edge, where solar particles would suddenly fade. Yet the cosmic ray readings were already changing. Around 2010, the spacecraft began recording a gradual increase in galactic cosmic rays. These were particles from outside the heliosphere, arriving from the wider galaxy. At the same time, some particles linked to the solar environment were beginning to decline. It was as if the outside was already reaching in. The final door had not opened, but something from beyond the door was already entering the room. That was difficult to fit into the clean model. In the simplest picture, the heliopause should mark the clearest change. Inside the heliopause, solar influence should dominate. Outside the heliopause, galactic particles should become stronger. Voyager was showing a more layered reality. The border was behaving less like a sealed surface and more like a region with pathways through it. The cosmic ray instrument on Voyager was built for exactly this kind of work. It counted energetic particles and helped identify where they came from. Every particle that struck the detector added another tiny piece to the map. Across months and years, the pattern became clearer. The galactic particles were rising before Voyager reached the confirmed boundary. This did not mean Voyager was fully in interstellar space yet. Other instruments still showed signs of the heliosheath. The sun's magnetic field was still present around the spacecraft. Solar particles had not fully vanished. The spacecraft was in a mixed region where the clean categories were beginning to blur. That blur was the important part. It meant the heliopause was surrounded by structure. It meant the galaxy did not simply begin on the far side of a sharp line. Its particles could reach inward along certain paths. Its influence could appear before the official crossing. The edge was beginning to leak. For a spacecraft, the change was measured as particle counts on an instrument. For the larger story, it meant the sun's shield had openings, channels, or connected regions where charged particles could move in ways the simplest models did not predict. The heliosheath was no longer just a waiting room. It was becoming a place where the inside and outside were already communicating. Voyager was still within the sun's outer bubble, but the galaxy was beginning to touch it. If cosmic rays from outside were already reaching the spacecraft, then something had to be connecting the heliosphere to interstellar space. The connection appeared in the magnetic field. In the summer of 2012, Voyager 1 entered one of the strangest regions ever measured by a spacecraft. Scientists began calling it the magnetic highway. The name was simple, but the idea behind it was deeply unusual. A magnetic field can guide charged particles. A charged particle is a tiny piece of matter with an electric charge, like a proton or an electron. When charged particles move through a magnetic field, they do not simply travel in straight lines. They spiral. They follow the field. They can be trapped, redirected, or carried along invisible paths. On Earth, this is part of why auroras appear near the poles. Charged particles from space follow Earth's magnetic field lines into the upper atmosphere, where they strike oxygen and nitrogen and create curtains of green, red, and violet light. Far beyond the planets, Voyager was seeing a much larger version of magnetic guidance. The spacecraft entered a region where particles seemed to move more freely along field lines. Some particles from the Sun were escaping outward. Some particles from the galaxy were moving inward. The same invisible structure appeared to be letting traffic move both ways. This was not what the simplest boundary picture had suggested. The heliopause had been imagined as the place where solar particles would finally give way to interstellar particles. But Voyager was seeing signs of connection before the final crossing. The inside and outside were not sealed apart. They were linked. The magnetic highway acted like a doorway through the edge of the heliosphere. It was not a doorway made from metal or stone. It was made from magnetic field lines stretching through plasma. Plasma is charged gas, so it responds strongly to magnetic fields. If field lines connect across regions, particles can travel along them like beads sliding along a wire. That is what made the readings so important. Voyager detected fewer low-energy particles from the solar environment. At the same time, it detected more galactic cosmic rays. Those cosmic rays had come from outside the heliosphere. They had crossed into the Sun's outer shield before Voyager had fully entered interstellar space. The spacecraft was still in a borderland. It had not yet seen the complete disappearance of solar particles. It had not yet reached the confirmed crossing. But the galaxy was already flowing into its instruments. The magnetic highway showed that the edge was not a simple wall. It was not even a clean curtain. It was a region of contact, a place where magnetic fields could open pathways through the outer heliosphere. A person walking toward the ocean might expect a hard line where land ends and water begins. But instead, they find marshes, channels, tidal pools, and wet sand. The boundary is real. The transition is also layered. Voyager was moving through the cosmic version of that layered edge. Behind it was the solar wind. Ahead of it was interstellar space. Around it were magnetic pathways, letting particles move between those two worlds. This helped explain why cosmic rays had risen too soon. They were not waiting politely outside the heliopause. They were finding routes inward, and solar particles were finding routes outward. The Sun's bubble was leaking in both directions. For scientists, this was more than a strange detail. It changed the way the edge had to be understood. A boundary made of plasma and magnetism can connect, fold, ripple, and shift. It can let particles through in some places while holding them back in others. It can behave differently depending on direction, solar activity, and the shape of the local interstellar magnetic field. Voyager had found that the outer heliosphere was not just a fading shield. It was an active magnetic structure. And the spacecraft was now moving through one of its open paths. For a short time, Voyager seemed to be traveling along the seam between the solar system and the galaxy. The particle counts kept changing. The cosmic rays grew stronger. The solar particles weakened. The edge was becoming less theoretical with every reading. Then, on August 25th, 2012, the pattern changed sharply. The solar particles around Voyager 1 nearly vanished. On August 25th, 2012, Voyager 1 saw the change scientists had been waiting for. The spacecraft was about 121 astronomical units from the center of the solar system. That placed it more than 11 billion miles from our star. At that distance, A radio signal from Voyager needed more than 17 hours to reach Earth. Nothing about the moment looked dramatic from the outside. There was no visible wall, no flash of light, no sudden image from a camera. The cameras had been turned off decades earlier, after the planetary flybys were finished. The discovery came through particle counts, tiny impacts, electrical signals, numbers arriving from a spacecraft so far away that every message was already from the past. For years, Voyager had been measuring two kinds of particles. One group came from the solar environment. These were lower energy particles linked to the Sun's own bubble of influence. The other group came from outside the solar system. These were galactic cosmic rays, fast particles moving through the Milky Way. Inside the heliosphere, solar particles were expected to be stronger. Outside the heliopause, cosmic rays were expected to rise. On that August day, the solar particles dropped sharply. They did not simply fade in a slow, gentle way. They fell away. At nearly the same time, galactic cosmic rays rose to a higher and steadier level. The spacecraft had moved from a region still filled with particles from our star into a region dominated by particles from the galaxy. This was the signal that mattered. The heliopause had been crossed. Voyager 1 had entered interstellar space. It was the first human-made object ever to do so. But the crossing was strange because Voyager was not moving through something solid. It was passing through a boundary made of pressure, plasma, particles, and magnetic fields. The heliopause is often described as the edge of the solar system. In this part of the story, that means the edge of the heliosphere, the edge of the solar wind bubble, the place where the flow from our star gives way to the local material between stars. Voyager did not leave the Sun's gravity behind. It did not pass beyond every object orbiting our star, but it crossed the boundary where the space around it was no longer ruled by the solar wind. That is why the particle data was so important. Before the crossing, Voyager was inside the outer heliosphere. After the crossing, it was sampling the interstellar medium directly. The interstellar medium is the thin gas, plasma, dust, and magnetic field between stars. It is almost impossibly empty by Earth standards. Yet it was strong enough to hold back the outward flow of the solar wind. Voyager had reached the place where those two environments touched. The moment was historic, but it did not become official right away. Scientists needed time to understand the data. They had to compare particle readings with magnetic field measurements. They had to make sure the spacecraft had not simply entered another strange layer of the heliosheath. For months, the interpretation remained uncertain. The particle data looked clear. Solar particles had dropped. Galactic cosmic rays had risen. Voyager seemed to be outside the Sun's plasma bubble. Then came more evidence from plasma waves. A burst from solar activity had traveled outward and caused the thin plasma around Voyager to vibrate. Those vibrations helped scientists measure the density of the material around the spacecraft. The density matched interstellar space. In September of 2013, NASA announced that Voyager 1 had crossed the heliopause on August 25, 2012. The crossing had happened more than a year before the announcement. For that entire time, Voyager had been drifting through interstellar space, while scientists on Earth worked to confirm where it really was. The particle data had opened the door. The plasma wave data helped prove what was beyond it. Voyager had crossed into the space between stars. Yet one expected signal refused to behave. The particles had changed exactly the way a crossing should look, but the magnetic field did something far more confusing. The magnetic field was supposed to help mark the crossing. Voyager carried an instrument called a magnetometer. A magnetometer measures the strength and direction of magnetic fields. It does not need light. It does not need pictures. It can sense the invisible field around a spacecraft as it moves through plasma and empty space. For scientists watching Voyager 1, this instrument mattered because the heliopause was expected to separate two magnetic environments. Inside the heliosphere, the magnetic field is carried outward by the solar wind. It comes from our star, but because the sun rotates, the field does not point straight outward like spokes on a wheel. It becomes twisted into a broad spiral. That spiral shape is called the Parker spiral, named after Eugene Parker, the physicist who helped explain the solar wind. Outside the heliopause, the magnetic field should belong to the local interstellar medium. That field is part of the larger magnetic structure of the Milky Way. It is extremely weak compared with a planet's magnetic field. Earth's surface field is tens of thousands of nanotesla. A nanotesla is a tiny unit used to measure magnetic strength. The interstellar magnetic field near Voyager is only a fraction of a nanotesla. But over huge distances, even a weak field can guide charged particles and shape plasma. So the expectation was simple. When Voyager crossed from the Sun's magnetic environment into the galaxy's magnetic environment, the direction should change. The particles had already changed. Solar particles had dropped. Galactic cosmic rays had risen. The plasma density later confirmed that Voyager was in interstellar space. But the magnetic field direction stayed surprisingly similar. It did not swing sharply. It did not turn in the clean way many scientists expected. It kept pointing almost the same way it had been pointing before the crossing. That was the confusing part. One set of instruments seemed to say Voyager had crossed the heliopause. Another important measurement seemed to say the boundary had not behaved like the model predicted. For months, this created debate. Maybe Voyager had entered a special outer layer. Maybe it was moving through a strange zone just inside the heliopause. Maybe the particles could cross before the magnetic field fully changed. Maybe the boundary was layered in a way no one had modeled clearly enough. The answer that emerged was more subtle. The magnetic field outside the heliopause appears to be draped around the heliosphere. Draping means the interstellar field bends and wraps as it meets the sun's bubble. A flowing river does something similar around a stone. The water does not pass straight through. It bends around the obstacle. In space, the local interstellar magnetic field can bend around the heliosphere, creating a direction near the boundary that looks more similar to the field inside than expected. That meant Voyager 1 could cross into interstellar space without seeing a dramatic magnetic turn. The field had changed environments, but the direction had remained close enough to hide the crossing at first. This made the heliopause feel much less like a clean border. A border on a map can be crossed in one step. One side has one name. The other side has another. But the heliopause is made from moving plasma, pressure, and magnetic fields. It can have layers. It can have pathways. It can have fields that bend around it. It can allow particles to change sharply while the magnetic direction changes gently or barely at all. That is why Voyager 1 was so important. It did not simply confirm the model. It revealed where the model was too simple. The crossing was real. The particles proved it. The plasma density supported it. but the magnetic field showed that the boundary was more connected to the galaxy around it than scientists had expected. The edge was not a sealed surface. It was a place where the sun's bubble and the local interstellar field pressed, bent, and adjusted around each other. Voyager 1 had crossed the boundary, but the boundary had refused to act like a clean dividing line. And 6 years later, Voyager 2 would reach the same kind of edge from a different direction, carrying the chance to test the mystery again. 6 years after Voyager 1 crossed the heliopause, Voyager 2 reached its own boundary. The date was November 5th, 2018. Voyager 2 was about 119 astronomical units from the center of the solar system. That means it was more than 11 billion miles away. Its radio signal took more than 16 hours to reach Earth. By the time scientists saw the data, the spacecraft had already been moving through that distant region for most of a day. This crossing mattered because Voyager 2 was traveling in a different direction from Voyager 1. Voyager 1 had moved above the plane of the planets after its Saturn encounter. Voyager 2 had followed the long Grand Tour route past Jupiter, Saturn, Uranus, and Neptune, then continued outward below that plane. The two spacecraft were separated by direction as much as distance. They were touching different parts of the same enormous invisible shell. That gave scientists something they had never had before: a second measurement of the heliopause. Voyager 1 had shown that the crossing could be confusing. Its particle readings changed sharply in 2012, but its magnetic field direction stayed surprisingly similar. Voyager 2 reached the edge with a different set of clues. Its crossing appeared more sudden. The flow of solar wind plasma around it dropped away. Galactic cosmic rays increased. The magnetic field changed more clearly than it had for Voyager 1, although still in a gentle and limited way. Voyager 2 also had a working plasma instrument. That was important. Plasma is charged gas, made of particles such as protons and electrons. A plasma instrument can measure the speed, density, and temperature of that charged material. Voyager 1's plasma instrument had stopped working long before its heliopause crossing, so scientists had to rely on other clues, including particles, magnetic fields, and plasma waves. Voyager 2 could measure the solar wind plasma more directly as it disappeared. That made its crossing especially valuable. For the first time, scientists could compare two passages through the edge of the heliosphere. The two crossings told the same large story. There was a real boundary. Inside it, the solar wind still shaped space. Outside it, the local interstellar medium became dominant. But the details were different. Voyager 1 crossed in 2012 at about 121 astronomical units. Voyager 2 crossed in 2018 at about 119 astronomical units. Those distances were close, but the spacecraft were moving through different regions at different times. The sun's activity had changed. The pressure of the solar wind had changed. The magnetic field geometry was different. The shape of the heliopause was not identical in every direction. This confirmed something Voyager had been hinting at for years. The edge of the heliosphere is a real place, yet it does not behave like a perfect shell. It has weather. It has structure. It changes with location. It changes with time. It responds to storms and quiet periods from our star. A strong period of solar activity can send pressure outward through the heliosphere. A weaker period can allow the interstellar medium to press inward. Those changes travel slowly across billions of miles. By the time they reach the heliopause, they are delayed echoes of solar behavior from months or years earlier. That means Voyager 1 and Voyager 2 did not cross the same boundary under the same conditions. They crossed two different parts of a living surface. Together, they showed that the heliopause is less like the outside of a glass sphere and more like the skin of a bubble moving through a current. The skin exists. It can be crossed, but it ripples, bends, thickens, thins, and shifts depending on pressure from both sides. The achievement was extraordinary. Humanity now had two direct measurements of the space beyond the solar wind. Yet, two crossings are still only 2 points. The heliopause surrounds the solar system in every direction. It stretches above and below the planetary plane. It wraps around the front of the sun's motion through the galaxy. It trails behind the solar system as it moves through interstellar material. Voyager 1 and Voyager 2 gave us proof that the edge was real. They also showed how little two paths can reveal about a vast, three-dimensional boundary wrapped around the entire solar system. Those two crossings changed what interstellar space meant. Before Voyager, scientists studied the space between stars from a distance. They used telescopes. They measured starlight passing through thin gas. They looked for fingerprints of hydrogen, helium, carbon, oxygen, and dust in the light from faraway stars. They built models from those clues. But Voyager did something different. It placed instruments directly inside the local interstellar medium. For the first time, a human-made spacecraft was no longer only looking outward from inside the solar bubble. It was touching the material beyond it. That material was thin, beyond ordinary imagination. A cubic centimeter of air near sea level contains roughly 10 billion molecules. A cubic centimeter of local interstellar space contains far less than one particle on average. Voyager measurements suggested a plasma density around a few hundredths of a particle per cubic centimeter. That means a box the size of a sugar cube, placed in interstellar space, might contain almost nothing. Yet almost nothing is still not nothing. There were particles. There was pressure. There was temperature. There were magnetic fields. There were cosmic rays moving through the darkness. Interstellar space had texture. It was not a perfect void. It was more like an extremely thin material spread across enormous distances. On Earth, that thinness would feel like emptiness. In space, over billions of miles, even a tiny amount of material can push back against the solar wind. This is one of the strange lessons Voyager revealed. The solar wind streams outward from our star for billions of miles. It fills the heliosphere with charged particles, but eventually, the faint pressure of interstellar material is enough to stop it. The galaxy does not need to be dense to hold back the solar wind. It only needs to be present across a vast area. Voyager also measured magnetic fields beyond the heliopause. The interstellar magnetic field near the spacecraft was extremely weak. It was far weaker than Earth's magnetic field at the surface. But charged particles respond to magnetic fields even when those fields are faint. Over huge distances, a weak magnetic field can guide cosmic rays, shape plasma, and bend around the heliosphere like water moving around a stone. Temperature in this region was also easy to misunderstand. The particles in the local interstellar medium can be moving as if they are very hot, but there are so few of them that they carry very little heat. Temperature describes how fast the particles are moving. Heat depends on how many particles are there to share that energy. A person exposed to that environment would not feel warmth from the gas. There simply would not be enough particles hitting the body to transfer much energy. This made interstellar space feel even stranger. It could be extremely thin and still have pressure. It could be extremely hot by particle motion and still unable to warm anything in the familiar sense. It could seem empty and still contain magnetic structure. Voyager was measuring a place that human senses were never built to understand. Its instruments turned that invisible region into numbers. The magnetometer traced magnetic direction. The cosmic ray detector counted fast particles from the galaxy. The plasma wave instrument listened for vibrations in the charged gas. Those vibrations mattered because plasma can ring. When a disturbance passes through it, the charged particles can oscillate, moving back and forth in a way that reveals the density around them. That lets scientists estimate how much plasma surrounded Voyager after the crossing. The numbers supported what the particle data had suggested. Voyager was no longer in the solar wind. It was in interstellar space. But this new environment was not silent. It was not a dead emptiness beyond the reach of our star. It had its own faint structure, and that structure could still respond to events from the solar system. Voyager had entered the material between stars. Then it detected something even stranger. The sun was still disturbing the space beyond its own bubble. It did this through waves, not ocean waves, not light waves. These were waves moving through plasma, the thin charged gas spread through interstellar space. When our star produces a strong outburst, it can launch a disturbance outward through the heliosphere. One kind of outburst is called a coronal mass ejection. That happens when a huge cloud of charged particles and magnetic field is thrown from the outer atmosphere of our star. Near Earth, a strong coronal mass ejection can disturb satellites, power grids, radio signals, and auroras. Farther out, the same kind of disturbance becomes a traveling pressure pulse. It moves through the solar wind. It pushes into the heliosheath. Then, after crossing billions of miles, it can reach the heliopause. By the time it arrives there, the eruption that created it may have happened months or years earlier. The solar system is so large that even a fast disturbance becomes a delayed message. When one of these pressure pulses reaches the heliopause, it can strike the boundary like a distant hammer. The solar wind cannot simply flow freely beyond the heliopause, but the impact can send a ripple into the interstellar medium. That ripple moves through the plasma beyond the sun's bubble. Voyager 1 was in the right place to detect it. The spacecraft carried an instrument called the Plasma Wave Subsystem. It was designed to measure waves in charged gas. It did this by sensing tiny electric field changes around the spacecraft. In ordinary language, it could listen to plasma vibrations. When plasma oscillates, its charged particles move back and forth. The frequency of that motion reveals something important. It tells scientists the density of the plasma. A denser plasma vibrates differently than a thinner one. So when Voyager detected these waves, it was not only hearing a disturbance, it was also measuring the material around it. In October and November of 2012, Voyager 1 detected plasma oscillations beyond the heliopause. Then another, stronger event appeared in April and May of 2013. Those waves helped confirm that the spacecraft was in interstellar space. The plasma around Voyager was denser than the solar wind plasma expected inside the heliosheath. It matched the thin material between stars. This was a strange kind of proof. A solar eruption from the inner solar system had traveled outward. It had reached the boundary. It had shaken the interstellar plasma beyond it, and Voyager, already on the far side, had detected the ringing. The sun's particles had stopped dominating the space around Voyager, but the effects of solar storms could still reach past the boundary. That made the heliopause feel less like a clean ending. It was the edge of the solar wind bubble. It was the place where Voyager entered interstellar space. But it did not erase every influence from our star. A bell can ring after it is struck. A pond can ripple after a stone falls in. The local interstellar medium could carry the memory of activity that began far closer to the center of the solar system. This helped reshape the meaning of the crossing. Voyager had passed beyond the solar wind. It had entered the material between stars. Yet the boundary behind it was still being pushed, shaken, and disturbed by events from the same star that launched the solar wind in the first place. The edge was real. The separation was real. But the connection had not fully ended. Crossing the heliopause did not mean Voyager had escaped every trace of solar influence. And that makes the phrase, leaving the solar system, much more complicated than it first seems. This is where the story becomes easy to misunderstand. Voyager 1 crossed the heliopause. That means it crossed the edge of the heliosphere. It left the region where the solar wind is the dominant flow of particles around the spacecraft. It entered the local interstellar medium, the thin material that fills the space between nearby stars. That crossing was real. It was historic. It made Voyager 1 the first human-made object to directly measure interstellar space. But the heliopause is not the final outer edge of everything controlled by our star. The solar system has more than one kind of boundary. There is the boundary made by plasma. There is the boundary made by magnetic fields. There is the boundary made by gravity. Voyager crossed the plasma boundary. It crossed the edge of the sun's solar wind bubble. But gravity reaches much farther. Every planet orbits because of solar gravity. So do dwarf planets, asteroids, icy bodies, and distant comets. Even far beyond Neptune, the pull of our star still shapes the motion of objects moving through the dark. The most distant of those objects are thought to belong to the Oort cloud. The Oort cloud is not a place Voyager can photograph. It is too faint, too cold, and too spread out. It is a vast predicted shell of icy bodies surrounding the solar system. These objects are thought to be leftovers from the formation of the planets more than 4.5 billion years ago. Many are made of frozen water, methane, ammonia, carbon dioxide, dust, and rock. They are the kinds of objects that can become long-period comets. A long-period comet is a comet that takes hundreds, thousands, or even millions of years to complete one orbit around our star. Some arrive from far above or below the plane of the planets, which suggests they come from a distant spherical reservoir rather than from the flatter region near Neptune. That reservoir is the Oort cloud. Its inner edge may begin around 2,000 astronomical units from the center of the solar system. 1 astronomical unit is about 93 million miles. Voyager 1 crossed the heliopause at about 121 astronomical units. So even after entering interstellar space, it was still nowhere near the inner edge of the Oort cloud. At its current speed, Voyager 1 will need about 300 years just to reach the inner Oort cloud. then it may need around 30,000 years to pass through it. That number changes the feeling of the whole journey. Voyager has traveled farther than any human-made object. It has crossed the boundary where the solar wind gives way to interstellar space. It has measured particles from the galaxy directly. And yet, by the scale of the full gravitational solar system, it has barely begun to leave. This is the strange double truth. Voyager is in interstellar space. Voyager is also still inside the distant gravitational reach of the solar system. Both statements can be true because they describe different boundaries. One is about particles and plasma. The other is about gravity and orbit. The heliopause is the edge of the sun's protective bubble. The Oort cloud is part of the far outer architecture held by solar gravity. One boundary is active, shifting, and shaped by pressure. The other is enormous, slow, dark, and spread across deep time. This makes Voyager's achievement feel larger, not smaller. It crossed one of the most important borders around our star. Then it revealed that beyond that border, the larger journey still stretches for tens of thousands of years. The spacecraft has entered the space between stars, but the full solar system still extends far ahead of it, and that means the crossing was not the end of the story. It was the first doorway into a much larger darkness. The first doorway into that darkness also helps protect everything behind it. The heliosphere is distant, invisible, and far beyond the planets. But it is part of the reason the inner solar system is not exposed directly to the full particle environment of the galaxy. Outside the heliosphere, galactic cosmic rays move through interstellar space. They are fast particles, often protons or atomic nuclei, carrying energy from violent events across the Milky Way. Some may come from supernova remnants, where the shock wave from an exploded star pushes particles to extreme speeds. Others may be shaped by magnetic fields that stretch through the galaxy. By the time they reach our solar neighborhood, they can be moving close to the speed of light. A cosmic ray is tiny, but it can strike atoms inside spacecraft materials, electronics, or living tissue. When one hits the upper atmosphere of Earth, it can create a shower of secondary particles. Those secondary particles spread downward like invisible sparks from a high-altitude collision. Most never reach the ground in a dangerous way, because Earth has several layers of protection. The heliosphere is the outer layer. Earth's magnetic field is another. The atmosphere is the thickest and most familiar shield. Together, they reduce the amount of radiation that reaches the surface. The heliosphere does not block every cosmic ray. It is not a perfect wall, but it scatters and slows part of the galactic particle flow before those particles can reach the inner planets. That matters for Earth. It matters for Mars. It matters for spacecraft moving between worlds. It matters even more for astronauts who would spend months or years outside Earth's magnetic field. A larger heliosphere gives the solar system a wider protective region. A smaller heliosphere allows more galactic particles to press closer inward. The size of that bubble changes with solar activity. During stronger periods, the solar wind can push harder against the interstellar medium. During weaker periods, the outside pressure can press farther inward. Over an 11-year solar cycle, cosmic ray levels near Earth can rise and fall as the sun's shielding strengthens and weakens. During quieter solar periods, more galactic cosmic rays can enter the inner solar system. During more active periods, fewer can reach the same regions. The changes are not simple, because solar storms can also create their own radiation hazards. But the larger pattern is clear. The behavior of the heliosphere affects the radiation environment around the planets. Across much longer time spans, the boundary may change for other reasons. The solar system is moving through the local interstellar cloud. That cloud is a region of thin gas and plasma around us in the Milky Way. If the Sun moves into a denser or thinner part of interstellar material, the outside pressure on the heliosphere can change. A denser region could squeeze the heliosphere smaller. A thinner region could allow it to expand farther outward. Those changes would alter how much galactic radiation reaches the inner solar system over deep time. For Earth's surface, the atmosphere and magnetic field still provide strong protection. But for the upper atmosphere, satellites, deep space probes, and future crews, the heliosphere matters. It is the first shield. It is the broadest shield. It begins far beyond the planets, but its influence reaches inward toward the places where life and machines are most vulnerable. This is why Voyager's measurements were more than distant curiosities. They were measurements of the protective boundary around our entire planetary neighborhood. Voyager showed that this boundary is larger, messier, and more active than a simple model suggested. It moves. It bends. It leaks particles. It carries magnetic pathways. It responds to storms from our star and pressure from the galaxy. Every future mission that tries to leave the solar bubble will have to pass through this same unsettled region. And Voyager has shown that the path outward is not just empty distance. It is an environment. Any future spacecraft leaving the heliosphere will have to cross the same kind of region. First, it would pass through the solar wind, where charged particles from our star stream outward at hundreds of kilometers per second. Then it would reach the termination shock, where that flow slows and becomes hotter, denser, and more disturbed. After that, it would enter the heliosheath, the wide outer layer where the solar wind is no longer smooth. Then, somewhere farther ahead, it would reach the heliopause. That crossing sounds simple when it is described as a route, but Voyager showed that every layer can move, ripple, and change. The boundary does not sit still. It responds to solar storms. It responds to quiet periods. It responds to the pressure of the local interstellar medium. It changes depending on direction. A future probe would not be crossing a clean doorway. It would be crossing a moving region filled with plasma, magnetic fields, energetic particles, and delayed waves from events that happened years earlier near our star. For a small robotic spacecraft, this is a scientific challenge. For a crewed spacecraft, it becomes a survival problem. Galactic cosmic rays are one of the biggest concerns. They are fast particles from outside the solar system. Some carry enough energy to pass through metal, plastic, and human tissue. A spacecraft leaving the heliosphere would move into a place where that radiation is stronger than it is inside the sun's shield. Astronauts would need protection. That protection might include thicker walls, water tanks arranged around living areas, special storm shelters, or magnetic shielding that imitates part of Earth's natural protection. Every solution adds weight. And in space travel, weight is never a small detail. More mass means more energy to accelerate. More energy means more fuel, larger engines, or a longer journey. Even an uncrewed probe has problems. Electronics can be damaged by energetic particles. Sensors can be confused by radiation hits. Solar panels become less useful as the spacecraft moves farther from the center of the solar system. Past Jupiter, sunlight is already much weaker than it is near Earth. Farther out, a mission needs nuclear power or another long-lasting energy source. There is also the problem of speed. Voyager moved slowly by interstellar standards. Its journey to the heliopause took decades. A future mission designed to reach the boundary faster might travel much more quickly. That would shorten the mission, but it would also change the danger. At higher speeds, tiny dust grains become more serious. A grain too small to see can carry damaging energy if the spacecraft hits it fast enough. A probe heading toward another star would need shielding, detection systems, and a careful understanding of the material ahead. Interstellar space is thin, but it is not perfectly empty. Voyager proved that. It has plasma. It has waves. It has magnetic fields. It has particles from the galaxy. It has traces of dust and gas spread across distances so large that even thin material begins to matter. Communication becomes harder too. Voyager's signal already takes many hours to reach Earth. A future probe beyond the heliopause would send back faint messages across billions of miles. The farther it travels, the weaker those signals become. Large antennas on Earth would have to listen for whispers from the dark. Commands would take hours, then days, then eventually years if a probe ever approached another star. That means future missions cannot depend on quick instructions from home. They would need to make more decisions on their own. Voyager gave us the first direct map of this crossing. It showed where the clean model was too simple. It showed that the edge of the heliosphere has structure, motion, and surprise. But the spacecraft that made that map is growing old. Its power is fading. Its instruments are being protected, one decision at a time. And the machine that taught us how to cross the boundary is now nearing the end of its voice. Voyager gave us the first map of the crossing, but the spacecraft that made that map is running on a shrinking supply of power. Each Voyager carries radioisotope thermoelectric generators. These are nuclear batteries that use plutonium-238. As that plutonium decays, it releases heat. The spacecraft converts some of that heat into electricity. There are no solar panels powerful enough for this distance. Voyager is far beyond the region where sunlight could keep its instruments alive. Its power comes from the slow fading warmth of radioactive material packed inside the generators decades ago. At launch, each spacecraft produced about 470 watts of electrical power. That was never a large amount. It was less than the power used by many household appliances. But it was enough to run the instruments, computers, heaters, radio transmitter, and guidance systems. Every year, the available power dropped. The plutonium kept decaying. The generators became less efficient. The spacecraft slowly had less electricity to work with. So NASA had to make choices. A spacecraft cannot keep every instrument warm forever. It cannot run every system at full strength forever. Engineers have spent decades deciding what to preserve, what to turn off, and what to let go. Voyager's cameras were shut down after the planetary encounters. They had done their work at Jupiter, Saturn, Uranus, and Neptune. Beyond the planets, there was no nearby world to photograph. The cameras became less important than the instruments that could measure particles, fields, and waves. Those invisible measurements became Voyager's new eyes. As the years passed, more instruments were turned off. Each shutdown saved power. Each saved what? Helped keep another part of the mission alive a little longer. The choices became more difficult as Voyager moved deeper into interstellar space. Every working instrument was precious. Every signal from the spacecraft was unique. No other mission had measured this region directly from the outside of the heliosphere. But the power budget kept shrinking. In April of 2026, Voyager 1's low-energy charged particles instrument was switched off. That instrument had helped study particles moving through the spacecraft's environment. It had been part of the story of solar particles, galactic particles, and the changing edge of the heliosphere. Turning it off was not a failure. It was an act of preservation. By shutting down one instrument, engineers could keep other systems alive. The magnetometer remained important because it measured magnetic fields. The plasma wave instrument remained important because it could detect vibrations in the thin charged gas around Voyager. Together, those instruments could still tell scientists something about the space the spacecraft was crossing. But the direction was clear. The mission was narrowing. The spacecraft was not dying all at once. It was fading, system by system, instrument by instrument, watt by watt. That slow fading gives Voyager a strange kind of mortality. It is a machine, but its life has stages. Launch, planetary encounters, the long cruise beyond the planets, the termination shock, the heliopause, interstellar space, and now the final years of direct science. On Earth, engineers still listen. They use the Deep Space Network, with large antennas in California, Spain, and Australia. Those antennas are placed around the planet so Earth can keep listening as it rotates. Voyager's signal is incredibly faint by the time it arrives. It has crossed billions of miles. It carries information from a spacecraft older than many of the people now studying it. A command sent to Voyager, one takes many hours to arrive. Then engineers must wait many more hours for the reply. Even a simple exchange stretches across almost 2 days. This is how the mission now feels. Slow, careful, patient. Every instruction must be planned. Every bit of power matters. Every remaining instrument has to justify its place on the spacecraft. Soon the data stream will fade beyond recovery. The magnetometer will fall silent. The plasma wave instrument will stop listening. The transmitter will no longer send its whisper toward Earth. But the spacecraft will not stop moving. Voyager will keep drifting after the instruments go dark. It will keep following the path written by gravity, assists from Jupiter and Saturn long ago. Humanity will stop hearing it. The journey will continue. The journey will continue in silence. Voyager will keep moving after its instruments stop measuring. It will keep moving after its transmitter can no longer send a signal home. It will keep moving after the last command from Earth has faded into the darkness behind it. There is no air in interstellar space to slow it down. There is no ocean of thick gas dragging against its frame. There is only the faint pull of distant stars, the thin material between them, and the long curve of its path through the Milky Way. Voyager will not travel quickly by the standards of the galaxy. It moves at only a tiny fraction of the speed of light. But it does not need fuel to keep drifting. Once a spacecraft is moving through near empty space, it can continue for extraordinary spans of time. Long after its power is gone, Voyager will remain a physical object, a frame of metal, a silent antenna, old instruments, wires, shielding, and gold-colored material designed for a mission that began in 1977. Attached to each Voyager is the Golden Record. It is a physical message from Earth, a copper record coated with gold, protected by a cover and marked with instructions meant for anyone who might one day find it. The record carries sounds and images chosen to represent our planet. It includes greetings in many languages. It includes music from different cultures. It includes natural sounds, such as wind, thunder, birds, and whales. It includes images of people, animals, landscapes, anatomy, mathematics, and the location of our world. The chance of anyone finding it is almost impossibly small. Space between stars is too large for ordinary comparisons. A spacecraft the size of a small car is almost nothing in a galaxy more than 100,000 light-years wide. Even passing close to another star is rare on human timescales. Voyager 1 is expected to pass within about 1.6 light-years of a small red dwarf called Gliese, 445 in about 40,000 years. That sounds close. But 1.6 light-years is still more than 9 trillion miles. Even near another star, Voyager would remain a tiny silent object moving through an enormous dark volume. And yet, the record matters. It was never only about the chance of being found. It was also a statement. It said that a species on a small planet had learned enough to build a machine, aim it outward, and send part of itself into deep time. Voyager became more than a probe. It became a witness. It witnessed Jupiter's storms. It witnessed Saturn's rings. It witnessed the first known volcanoes beyond Earth erupting on Io. It witnessed the strange outer boundary where solar particles fade and galactic particles rise. It showed that the edge of the heliosphere was farther, more active, and more layered than the simple models had suggested. The boundary was not a clean wall. It moved with solar activity. It changed with direction. It leaked particles along magnetic pathways. It carried waves from eruptions that began far closer to our star. It protected the inner planets from part of the galactic radiation flowing through space. It marked a real crossing, but not the final end of the solar system. That is what Voyager detected at the edge. Not one simple line, a living border, a shifting shield, a place where the sun's influence and the galaxy's pressure meet in darkness. Soon, the spacecraft will stop telling us what it finds. The instruments will fall quiet. The signal will disappear into the background noise of space, but the object itself will keep going. For thousands of years, it will move toward the distant Oort cloud. For tens of thousands of years, it will pass through the farthest icy reach of the solar system. For millions of years, it may drift through the changing star fields of the Milky Way. By then, the mission will no longer be active. It will no longer be science in the usual sense. It will be an artifact, a silent piece of Earth moving between the stars. Voyager began as a spacecraft built to study planets. It became the first messenger to cross the sun's invisible boundary, and in doing so, it revealed something humbling about our own cosmic neighborhood. Even the edge of the place we call home is still moving, still changing, still protecting us, and still not fully understood.